This video cast continues our discussion on solutions. Now that we know how solutions are made and some of that specific vocabulary, we're going to continue with that a little bit more. And we'll start with talking about solute-solvent interactions. How will I know if one substance will dissolve another without actually trying it first? Well, we have a little saying in chemistry that I actually didn't make up. We use it all the time. And the phrase is like dissolves like. So polar solvents will dissolve polar solutes. Nonpolar solvents will dissolve nonpolar solutes. So like dissolves like is a very, very important phrase to remember when we talk about whether something will dissolve something else or not. Now, what about ionic? We don't generally have ionic solvents. So are they soluble by polar things, polar solvents, or nonpolar solvents? Well, the answer is that ionic compounds are generally soluble in water because water is polar. Now, so polar will dissolve ionic compounds. The reason why is because we have charged ends on water. Because water is polar and has that slight positive and that slight negative on that water molecule, it will attract the ions of the ionic compounds. And in the last video cast, we watched an animation and looked at several diagrams that showed you those hydration shells. And since those water molecules keep the ions separated, it does dissolve an ionic compound. Do you think that nonpolar solvents would dissolve something ionic? If you said no, then you're right. Ionic compounds are not generally soluble in nonpolar solvents because there's no charge to a nonpolar solvent. So there's no attraction, and so they just separate from one another and will not dissolve. So a better way to talk about like dissolves like is charged dissolves charged. Things that have slight or full charges will dissolve other things that have slight or full charges, and things that have no charge will dissolve things that have no charge and nothing else. You may have had a situation with this, like trying to clean up oil-based paint. If you've ever used oil-based paint and at the end tried to clean up, if you put that paintbrush under water, it does no good because oil is a non-polar substance. So what you end up you end up just making your sink more and more dirty with that oil-based paint when you try and clean it out with water. What you have to do with oil-based paints is you clean it with something that's also non-polar. So you'd use something or slightly polar like gasoline. Most people will use gasoline or kerosene to wash off their hands and get that oil-based paint off their hands. It will also get it off the paintbrush. And then once you get the paint cleaned off, then you can wash them with water to get rid of the gasoline or kerosene smell. Another one would be those sticky backs to like stickers, price tags, and things like that that get on top of things. If you want to remove that, that adhesive is non-polar. So you've got to use something else that's non-polar. A really great thing to use for some things is WD-40. If that's a little too harsh, then you would want to use something like vegetable oil. You can use vegetable oil. It will dissolve the adhesive, and then it's much easier to remove that sticker. All right, so liquid solute solvent interactions. Immiscible means that the solute and solvent have opposite polarities and no hydration occurs. They are not soluble in one another. Oil and water is immiscible. And you can probably see it from where you're sitting right now, but if you look at this test tube, we have two substances. We have water and methylene mixed together. And you can see the distinct line in between those two. They're right here at this point. So this thing has two meniscuses. I don't really know how to say that in plural, but anyway, we've got two of them right here. And then you have the one at the top. And they will stay separate. If we look at the particle model, you can see we have this definite line of difference. We've got water up above it and methylene down below it. Now we can tell a few things by this particle model. You know that water is polar. So methylene must be nonpolar. So there's no attraction, and so they don't mix. The other thing we can tell is the comparative densities. Which one's more dense? The methylene. How do we know? It's at the bottom. All right. Now, if that's what immiscible is, where they are not soluble in one another, then what's miscible? They are soluble in each other. So the solute and solvent have the same polarities, and hydration occurs. So we have this picture down here. We have acetone and water. So water and acetone are attracted to each other, and so you can see the acetone particles here floating around in with the water molecules. They're not separate. So there must be some sort of attraction between those two. So we can assume that acetone is also polar. It is very slightly polar, but it is technically polar. Here I have another example where you have benzene and carbon tetrachloride. Carbon tetrachloride is a non-polar solvent. So if benzene is miscible in carbon tetrachloride, then benzene must also be nonpolar because like dissolves like. Solutions at equilibrium. So at equilibrium, so we're going to talk about this again, and again building up to our equilibrium chapter. What's equal about equilibrium is equal rates. This would come into play, and you probably had this experience if your mom helped or let you make Kool-Aid as a kid. So, you know, the recipe or the package says half a cup of sugar, but you like things sweet, so you put more than that in your Kool-Aid. And then you're stirring and stirring and stirring, and the sugar will not go into solution. It's just sitting there on the bottom. No matter how much you stir, it sits there. Well, we've reached its solubility. The solvent can't support any more solute being dissolved. And that sugar that looks like it's just sitting there is a little more dynamic than what it appears. And dynamic means that it is actually changing. So what we actually have happening is we've got some of those solute particles, the sugar on the bottom, are dissolving. But the solvent can't hold that much. So at the same rate that some dissolve, others crystallize into the solid form. And so you do constantly have sugar on the bottom, but it's not the same particles. It's ever changing. Some of it's dissolving, some of it's recrystallizing, but they're happening at the same rates. I have this picture. This is more of a liquid vapor thing, but I like the little cartoon. So remember with the liquid vapor in the water bottle, that equilibrium, we had some of the particles that were escaping to the vapor phase, and then they would lose energy, and then they would condense back down, and then others would evaporate at the same rate. Effects of pressure on solubility. Increasing pressure increases gas solubility in liquids. So if you have a soda, the reason why when you buy a new soda you cannot squeeze that bottle at all, and that's because it is sold under pressure. We force that carbon dioxide into that liquid and make it stay there with pressure. And as soon as you open the lid on a new bottle of soda, you hear that shh, and that's that sound of releasing pressure, and then the bubbles start to appear. And that's because with pressure being released, then the solubility is also decreased, and the bubbles start coming out of solution. And if you were to leave that bottle open with the lid off, then it would be flat very, very quickly, because low pressure, it would decrease that gas solubility. Pressure has very little effect on the solubilities of solids and liquids. Here we can see a nice little picture here. We've got our gas, those are the red particles, and then we have our liquid there that's kind of a light blue with the black particles in there. And as we increase pressure and push down those particles, we force them into solution. This is Henry's law. It does apply to gas-liquid solutions at constant temperature. So increasing pressure does increase solubility of gases. So the solubility of the gas in a liquid is directly proportional to the pressure of the gas above the liquid. carbonated beverages, like I just said, the carbon dioxide is forced into solution by increasing that pressure. Now that after we release the pressure and we hear that shh, and we see the bubbles, this is called effervescence. This is the escape of a gas from a gas-liquid solution. So you can think about opening a soda that is a gas-liquid solution. You decrease the pressure, and then the gas starts to escape from that solution. Okay, now we're going to learn how to read some solubility curves. These are very often on your final exam and are very, very important for you to understand. They are going to map out the maximum amount of solute that a solvent can hold at a range of temperatures. So there is a limit to the amount of solute that can be dissolved. Just going back to that example with the Kool-Aid. You put too much sugar into the Kool-Aid, it can't dissolve, so it looks like it just sits there. We've reached its maximum amount. We've reached its solubility limit. When we have reached that limit, we would say that the solution is saturated. And we have to know the difference between these three terms: unsaturated, saturated, and supersaturated. Saturated, if you think about, if I say this paper towel is thoroughly saturated, what does that mean to you? It should mean that it is full of water and I can't pick up any more water with that paper towel. It is full. Well, a saturated solution is the same way. It is going to be, it can't hold any more solute. It is full. If you put more in there, it's just going to sink to the bottom. So unsaturated means that we could put more in and dissolve it. All right? Supersaturated means that we have tricked it into holding more solute than it should at a particular temperature. And we do this a lot if you've ever made rock candy before. You make a supersaturated solution of sugar, and then you let it kind of cool down very, very slowly. Then you would introduce like a sea crystal or something of that sort, like a string, and you put that into that solution, and all of a sudden these sugar crystals start to appear on the string. That's what happens with when you disturb a supersaturated solution. I do have a little video of a supersaturated solution, and we're going to disturb it. So it's here and here. I had it pulled up. All the ads. All right, here we go. He has a supersaturated solution, and the way this is done is you take something to a pretty high temperature. So you take water to a pretty high temperature, and then you put as much solute as you can in there and let it dissolve. And you keep adding until you get some on the bottom that will not dissolve. Then you take that hot solution and you pour it through some filter paper to get rid of all those extra little particles that are there on the bottom. And then you let it cool undisturbed for a good period of time until it's cool. And we've tricked it into holding more than it should. If you do this improperly and just let it cool down, but there's too much movement or you're knocking the beaker, then that extra stuff that the solvent can't hold will precipitate out. So what he's doing here is he's going to take a little piece of the solvent or solute and drop it into this container. And you're going to start to see, there it goes, mass crystallization. So the solid just precipitates out of the solution and becomes a solid. All right. It also gives off a lot of heat because you got a change in attractive forces there. You're breaking the attraction between the particles, and it does produce heat. All right. So now, go back to this. So now we know what saturated is, and on a graph they show you a saturated solution. The level, if it's on the line, it is a saturated solution. Unsaturated solutions, the amount you could add more, so you're below the line on the graph. And supersaturated solutions, you're above the line on the graph. Now, solubility is determined experimentally, and someone's compiled all of this information for us at various temperatures. It has strange units, and because it has strange units, the state will use those units against you and will ask you very tricky questions, so we're going to try and master those. It gives you how many grams of that solute will dissolve in 100 grams of water, or remember the density of water is 1 gram per milliliter, so 100 milliliters of water. So these will be, usually what you're going to do is you're going to look at temperature in order to decide whether something is soluble or not. So let's have an example. So say we're looking at potassium chlorate. So potassium chlorate, and we want to know its solubility at 50 degrees C in 100 grams of water. So we would go to the temperature, 50 degrees, right down here, and we will go up until we find potassium chlorate. And it's right here where it hits that line. That is the limit for a saturated solution. So then I will go over here, and it says that 20 grams of potassium chlorate will dissolve in 100 grams of water. All right, just reading the graph. A tricky type of solution would be, or a tricky type of question would be, how much potassium chlorate do I need to add to 200 grams of water at 50 degrees C to get a saturated solution? Okay, well, again, you would read the graph, and at 50 degrees C, 100 grams can support, or 20 grams can be supported by those 100 grams of water. So for 200 grams, you just double it. So 40 grams would be able to be dissolved in 200 grams of water. If they said how much would be dissolved in 300 grams of water, the maximum amount, then it would be 3 times 20, which would be 60. Another type of question would be asking for your whether a solution is saturated or unsaturated. I'm going to kind of use the same example. And what if I had 15 grams of potassium perchlorate dissolved in 100 grams of water? Well, 15 grams is going to be about right here. And at this temperature, could I put more solute in? Yeah, I can go all the way up to 20. So this would be described as an unsaturated solution. If I said I had 35 grams of it dissolved in 100 grams of water, then that would put it way up here at 50 degrees C. And so this would definitely be a super saturated solution. And if it's on the line where we've dissolved 20 grams in 100 grams of water, then it is a saturated solution. All right, and as you see, as this graph, for most of these substances, as temperature goes up, most of these lines also increase. So for most substances, as temperature increases, so does their solubility. But not all of them. You'll see a couple that go the other way. We'll talk about that. All right, but first I want you to try and read from the solubility curves and answer these two questions. So problem number 1. If a saturated solution of potassium nitrate in 100 grams of water at 60 degrees C is cooled to 20 degrees C, approximately how many grams of the solute will precipitate out of the solution? Well, in a question like this, what we want to do is we want to see what the solubility is at these two different temperatures. So first, let's go to 60 degrees C. And this is potassium nitrate right here. All right, at 60 degrees C, I go up, and I would say that my solubility is right around, it looks like it's a little over 100. So maybe it's at 101 grams will dissolve in 100 grams of water. Now I'm going to cool that down to 20 degrees C. At 20 degrees C, potassium nitrate, let's see, it's going to be about right, oops, I'm a little off, about right there. So let's say maybe what, 33? All right, so this is at 60 degrees C, and I got that off the graph. And at 20 degrees C, the water can only hold 33 grams. So at 60 degrees C, it held 101. At 20 degrees C, it holds only 33. So the difference between those two must be how much precipitates out, because at 20 degrees C, the solvent just can't hold that much more solute unless we trick it, and in this case, we're not tricking it. So you would just subtract those two numbers. And so you're going to end up with, let's see if my mental math works, 68 grams of your potassium nitrate would precipitate out. And we would see that sitting on the bottom of the container. All right. Now, the next question, how many grams of sodium nitrate will be needed to dissolve in 200 grams of water to form a saturated solution at 40 degrees C? So for this one, we're going to look for sodium nitrate, and it's up here. And we're going to go at, our temperature is 40 degrees C. Notice I always start with that temperature. And I go up and follow this line until it crosses this line. So that's my point right there. And I will go over here, maybe in a straight line. And I see that it's maybe around 105 grams per 100 grams of water.
Come to the office. Caleb Pittman, please come to the office.
So 105 grams can dissolve in 100 grams of water. So how much will dissolve in 200 grams of water? Double that. So 210 grams of sodium nitrate will dissolve in 200 grams of water. Now, the dotted lines are gases on this particular graph. And notice what happens to the solubility of gases as temperature goes up. Those are the ones where the solubility is tanking. So, the solubility of gases decreases with increasing temperature. Now, what does that mean for you and your sodas? The best way to keep them fizzy longer is to keep them in the refrigerator. Keep them cold. And the gas will be more likely to stay in solution, and also keep the cap on securely to keep the pressure from escaping, or the gas from escaping. So, as temperature increases, gas solubility decreases. And that's important. A lot of times what they'll have on a final exam or something like that is they'll have this graph, except the dotted lines will also be solid. And so what you're going to, and then they would ask you, which one of these is most likely a gas? And you're going to look for the ones that as temperature increases, their solubility decreases. Now, as temperature increases, like we talked about a minute ago, the solubility of most solids increase. And you can see that from this graph. Okay, I'm going to stop there, and we'll pick this up in the next video cast.